Imagine trying to convince someone you know the exact password to a digital vault without ever typing it in or saying it out loud. That is the core paradox of digital cryptography. You have to prove you hold a specific piece of information without ever revealing the information itself. To understand how computer scientists approach this, look at this animated map. It represents a standard test case called the three-coloring problem. You are given a grid of regions, and you have to fill it using exactly 3 colors. The only rule is that no 2 borders touching each other can ever share the same color. If you want to prove you solved it without showing your work, you use an interactive zero-knowledge proof. You mask the map. A verifier picks any 2 touching regions, and you reveal just those 2 to show they are different. You cover them back up, scramble the color layout, and repeat this guessing game hundreds of times until the verifier is statistically convinced you aren't just getting lucky. The flaw here is that this process demands constant, real-time communication. A prover and a verifier have to pass information back and forth. You cannot simply write down a static proof, hand it over, and log off. But for internet security to actually scale across billions of users, that is exactly what we need. A password system has to rely on a static, independently verifiable document that completely locks away its underlying secret without needing an endless conversation. In 1994, cryptographers Oded Goldreich and Yair Oren published a theorem that shut the door on that idea. They mathematically eliminated the possibility of a static zero-knowledge proof. The researchers proved that any proof skipping that interactive back and forth automatically leaves a trail of data. A static document inherently contains enough information that a third party could eventually reverse engineer it and extract the secret. Because this was an absolute mathematical ruling, research into static zero-knowledge proofs completely stopped for the next 3 decades. So computer science accepted a permanent compromise. If you wanted the absolute security of zero knowledge, you had to interact. If you wanted the convenience of a static document, you had to surrender zero knowledge. In 2023, Rahul Ilango, a graduate student at MIT, was studying a highly obscure theoretical subfield called proof complexity. Instead of looking at how hard it is to solve mathematical problems, proof complexity asks how hard it is to actually prove the solutions are correct. The foundation of this field goes back to logician Kurt Gödel. In 1931, Gödel proved that within any mathematical system, there are statements that are undeniably true, but inherently impossible to prove. These statements aren't factually false, the math holds up, but confirming them would require a proof so staggeringly complex and long that humanity could never actually write it down. For all practical purposes, the proof is unknowable. Mathematicians usually view these unprovable truths as frustrating boundaries. Ilango recognized that in the world of digital security, an absolute inability to prove something is an exploitable structural loophole. Think of it like buying a heavy steel lock for a vault, but instead of a guarantee that the lock is unbreakable, the packaging comes with an admission. The lock might have a flaw, but absolutely no one will ever be able to prove that flaw exists. If a vulnerability is mathematically impossible to prove, it cannot be exploited by an attacker. In cryptography, an unprovable flaw is functionally identical to perfect security. Ilango took the standard static proof for the map coloring problem and added a caveat. He wrote that the map is securely colored, assuming standard mathematics contains no discoverable contradictions. That specific assumption is generally accepted as true, but it falls into the category of statements that take too long to ever actually prove. Adding this unprovable caveat shifted the proof into an alternate mathematical reality, one where the rigid 1994 impossibility rule simply no longer applied. Ilango defined this state as effective zero knowledge. The proof doesn't guarantee a leak is impossible, it just relies on the certainty that nobody will ever have the computing power or the time to prove a leak exists. By embedding this logical hurdle directly into the code, Ilango bypassed a physical limitation of data with an abstract rule of mathematics. This shift creates a path for programmers to build systems where a piece of data serves as a one-sided proof. Because a verifier cannot prove the system's underlying math is consistent, they cannot mathematically distinguish the secret proof from a simulation. This makes the document effectively secure without the need for a live conversation. For decades, the study of what mathematics cannot do was entirely isolated from the practical engineering of computer security. Theoretical limits stayed in textbooks, while cryptographers built everyday software. Ilango's work crashed those two worlds together, forging the most abstract concepts of mathematical logic into a functional tool for modern digital cryptography. Theoretical dead ends and logical gaps now serve as practical tools for information security. The same logical boundaries that once troubled Gödel now provide a technical shield for digital secrets, turning the inability to prove a statement